So my background has absolutely nothing to do with the talk. My background is actually Comet Assassin. And it was a lot of fun getting the whatever responsible committee it is to finally accept that they would have a Comet Assassin. They were very unhappy with the idea of that name initially, but that's a different story. So we're talking about some games you can play with Galactic Supernova Remnants to understand the binarity or any higher order system associated with exploding stars. And then also that you can start to look at the progenitors of the stars that exploded in galactic supernova remnants. And most of this is enabled by Gaia, like many things. Actually got into this sort of backward or sideways or something, that there were a series of external supernovae called type 2b supernovae. So this is where you initially see hydrogen lines, and then the hydrogen lines go away, and you see helium lines. So it transitions from a type 2 to a type 1b. And there are a lot of claims that these things could only be formed by binary interactions. And even claims that people were seeing the binary companions in these distant galaxies, which is dubious, but anyway. But sort of remembered or realized is that Armin Rest actually had a spectrum of the Cas-A supernova, thanks to the beautiful little trick of dust reflection spectroscopy. And Cas-A was a type 2b supernova. And it's also really easy to go and look at Cas-A and see if it was a binary or not a binary. And so that's sort of then led to this series of projects. And so I won't really do it historically, but we'll try to put it together. So we'll talk about binaries, a little bit about triples, and then this idea of doing progenitors of supernova from the local stellar populations. So, of course, most of these massive stars are in binaries. In fact, a very large fraction of them are in higher order systems. There were a series of very nice studies on this over the last few years. And as soon as you put these things into binaries, they start to interact. A significant fraction that will merge, a significant fraction that will transfer mass. And you have to understand all of this to build into things like binary population synthesis models. And you depend on the binary population synthesis models for everything from how many of these different supernova types do you get, how many LIGO merger systems do you get, and so forth. But the problem is these contain many uncertain bits of physics like common envelope and things. And you can get very different answers by playing with the knobs. And then furthermore, essentially everything we know about neutron stars and black holes comes from systems which are interacting or merging binaries. I mean, the exceptions are there are pulsar binaries. But certainly for black holes, unless it's interacting or merging, you don't know anything about what's going on. But both interacting and merging systems are a tiny fraction of all compact object binaries. And the fraction of massive star binaries that end up as LIGO mergers is something like 0.1%. And so if you want to get a better handle on these properties, is you would like to understand, say, the binary properties at the time the stars are exploding. And that's basically the game you can play by looking at the remnants. Triples are interesting because they can dramatically change the evolution of binaries through Kozai-Lidov and its various extensions. It can basically drive otherwise non-interacting binaries to interact. It can drive coalescences and mergers on much, much shorter timescales than you would guess from a binary model, and to the extreme, which was in part pioneered by Doron Kushner and Subo Dong when they're at the Institute, of driving them to very high eccentricity, and you can get essentially a direct collision driven by the presence of a third body. But the multiplicity of supernova progenitors can, when they're dying, can really only be studied in the galaxy. There are a lot of problems with doing it in external galaxies. Generally, the companions are main sequence stars, which are much, much fainter than the star which exploded and hard to see. People believe, there's sort of mixed camps on this, that supernovas form a fair amount of dust. If they do form a fair amount of dust, that surviving binary companion is buried by the dust for some decades or centuries, even if it is present. And in theory, you could see if it wasn't obscured. And it's just very hard to study what's going on there. And then also, of course, if you are doing this in an external galaxy, you'll essentially never know the outcome of the explosion. Whereas in the galaxy, you frequently will know what the outcome was, a neutron star, and sometimes there's evidence of it for a black hole. And so you also get the connection of explosion and outcome. Progenitors, well, you know, there are various people who try to blow up stars. And, you know, if you say, dearest, kindest theorist, please blow up my star, sometimes they manage to do it and sometimes they don't manage to do it. But part of the problem is if it does explode, you know, was that really the right answer for that star? And if it doesn't explode, was that the right answer for that star? The only way to really determine these things is to be for certain is to experimentally do the mapping between progenitor stars and outcomes. And that's the only way we'll really know whether simulations are getting the right answers or not. And so it's an important way of doing this is to look for the progenitors of supernova. This has basically been done in external galaxies by direct observations. It's a tough road. There are less than 20 done because basically it depends on having archival Hubble data of the site of the explosion. Usually there are only 1 or 2 bands of Hubble data. And in theory, you need to constrain a luminosity, a temperature, and extinction. And last I heard, in order to measure 3 numbers, you need at least 3 numbers measured. And so there are considerable uncertainties in the properties of the progenitor. If you can pin down the luminosity, you are relatively safe as to the mass, because the mass is still largely, or the luminosity is still largely determined by the helium core mass, and that is still largely determined by the initial mass, even in the presence of moderate effects from binaries. The other thing you can try to do in external galaxies, and there are quite a few papers on this, which is why I've just stuck it into Del Canton group and Badena's group, is you take a patch around an external supernova remnant or an external supernova, and you analyze the stellar population to determine the local star formation history. The local star formation history is a function of time, gives you a probability distribution for which star will explode, and so you can try to infer the masses of progenitors and then the mapping between stars and who explodes more statistically.
I have a question from...
Just one quick question. What's the emission process in core collapse supernovae? What is actually making the light?
In the core collapse supernova, what you see is mainly driven by recombination and a little bit of radioactives. You don't actually see the initial thermal emission from the explosion. That all gets PDV'd away. Basically, stars are too small to efficiently radiate the initial energy. And so what you see is the energy from the limited amount of radioactives produced by core collapse, and then also just recombining 10 solar masses of hydrogen and helium. Okay, so if I have a star in a binary, and then I blow up one of the members, there are 2 effects which change the binary. The first one goes all the way back to 1961 to a paper by Blau. I'm not sure I'm pronouncing that right. But basically, as you know, now we like to give this to all of our students, and you can just work out is that for any binary orbit, if you impulsively eject half of the mass, the over half the mass, the binary becomes unbound. If you keep more than 50% of the mass, the binary remains bound. And so usually, since you were blowing up red supergiants in the type 2p supernova, you do eject quite a bit of mass. And so just from this effect alone, a lot of binaries will get disrupted. The second realization is once people started to find neutron stars and pulsars, is you would find that some of them are really moving. And a typical model now, we picked a somewhat random one of Hobbs in 2005, is their model for modeling the kicks to neutron stars on formation is 265 kilometers Gaussian in each of the 3 dimensions. So the total kick is √3 bigger than that. And so you see neutron stars flying away from their explosion sites at even up to 1,000 kilometers per second. And needless to say, that will also contribute to binaries becoming unbound. And if you put these 2 things together, in fact, most binaries don't survive the explosion. If you do disrupt the binary, then the other star in the binary goes floating away. And this is actually a long-standing idea of people looking for runaway O and B stars as possibly being survivors of an unbound supernova binary. Recent studies have coined the term that really they're more walkaways than runaways, the typical velocity you get from disrupting the binary is less than people really thought. And the simplest way to think about it is the majority of supernova explosions are of red supergiants, and the orbital velocity around a red supergiant is not that high. Right? You can only get a high velocities if you're in a relatively smaller orbit around a stripped star. And so when you do the numbers, you get the typical velocity of the star running away is less than 30 kilometers per second, which is not that dramatic even for O and B stars. So anyway, here's a result of someone's binary population synthesis model of this process by Renzo in 2019. This was in fact one of these papers looking at just how fast the runaway stars go. When you start up here with everyone in binaries, about a quarter of them merge. Oops. About a quarter of them merge before anything explodes. Okay, so 80% aren't mergers. When they explode, 86% of them are disrupted, only 14% remain bound. And in their model, it's about, of the ones that are bound, about 2/3 are black holes, 1/3 are neutron stars. So the total number of black holes formed is lower than the number of neutron stars, but in most of these models, you are ejecting less mass with the black holes. And they also, in the black hole formation, they assume the kicks are smaller than the neutron stars. Since we have no really good evidence on how much of a kick there is in black hole formation, this is all a little notional. And then if it's broken up, about 3/4 of the time, the companion that's drifting away is a main sequence star. And then this is their focus of their paper, is that most of them are moving less than 30 kilometers per second. And then some of them have post-main sequence, ranging from various degrees of stripping all the way down to being a white dwarf. But the main point is if you just look at the big picture, in this case, 22% merge prior to the explosion, 86% of the binaries which survive are disrupted, and only 10% of the initial binaries are still binaries after the first star explodes. So most binaries do not survive to ever get to forming a second compact object. That's one reason why, that's one of the many regions why the LIGO mergers are such a biased sampling of compact objects, is that almost none of the binaries survive even to worry about whether you're going to eventually get two compact objects. So why search supernova remnants? They give you a very well-defined place to look, right? It's sort of someone has sat there and said X marks the spot for where the explosion was. They can be selected sort of in a sort of uniform way in time, right? As you can see a supernova remnant for something approaching 100,000 years. And if the statistics get good enough, you'll have to worry about the fact that the visibility lifetime of the supernova remnant does depend somewhat on the properties of the explosion. But right now, the statistics are so crappy that you don't have to worry about that. You can look both for bound and unbound systems, right? Because basically you know where to look, and basically the way to think about it is the supernova remnant is expanding at the speed of the explosion, okay? And nothing associated with the neutron star and the binary is expanding at anywhere near the speed of the explosion, okay? And so the compact object, the surviving star, the surviving binary are all sitting down there somewhere close to the center of the supernova remnant, okay? And there are the odd exceptions where you have these neutron stars tearing away at 1,000 kilometers per second, but they're the minority, as you sort of know where to look for it. And so in theory, you can plausibly do statistics, okay? It's, my colleagues in the statistics department would probably be horrified, but generally they're horrified by anything I call statistics, so that's not really much I can do about that. Okay, so first you can think about looking for bound companions. Bound companions are really simple if someone has identified the compact object. And that is, you just look at the compact object and see if it's got a star associated with it. And so the picture at the bottom left is the center of the Cas-A supernova remnant. Okay, there is the location of the neutron star. Okay, this is just a pan-stars 1 image. I think you'll agree there is no one in the hole at the neutron star. And so Cas-A was not a binary, okay, or is not a binary now. And so you can do this if you start with, you can sort of plausibly, you can select 49 supernova remnants where you could plausibly do the search. Only 23 of them have identified compact objects. Okay, and the problem with most of the rest, which I'll come back to towards the end, is X-ray source confusion. 3 of them are binaries. 3 of the compact objects are in binaries. And since you know exactly where to look, you can typically set limits on any stellar companion to the compact object down to a few tenths of a solar mass. And even in the worst case, you would get a limit of like 3 solar masses. And so the answer for this case was that of the 23 compact remnants, there are the 3 binaries and no one else is a binary. So the 3 binaries were previously identified. Okay, and here are the 3 systems. One is the famous SS433, which is a Roche-accreting black hole system. You know, there's still some debate about black hole or not black hole, but I'd say the overwhelming consensus is that SS433 is probably a black hole system. And then there are 2 neutron star high mass X-ray binary wind accretion systems that were found by Hess and Fermi, respectively. It's interesting that all of the binaries in supernova remnants are interacting. Right? There were no non-interacting binaries in the supernova remnants. And we at least floated the following possible explanation for why you might find a lot of wind accreting systems is when the supernova goes off, the shock does smash into the companion star. And it has to be pretty close in to have a visible effect on the companion star in the sense of making it overluminous for an extended period of time. If you put it close enough, you can greatly enhance the luminosity of the star for a while. Basically, you puff up the envelope of the star, and then as it Kelvin-Helmholtz contracts, you get the luminosity from the contraction. But that usually doesn't last that long, centuries, not thousands of years. And it does require a quite close binary. And so, for example, basically, if you do this with a companion to a red supergiant exploding, you basically don't expect really to see anything because the companion subtends, sort of no solid angle in terms of absorbing the energy of the explosion. But you can imagine that if you might have a much more subtle effect, is just that you get enough heating of the outer layers that it doesn't do anything dramatic, but it essentially enhances the stellar winds for some extended period of time. And that might give you a sensible way to have lots and lots of wind accretion binaries associated with supernova remnants for 10,000s or tens of thousands of years. But no one's actually gone beyond that idea, just the idea of someone has to sit down and actually see if that's a sensible thing to happen. All right, unbound companions are harder because now you have to look not right on top of the compact remnant. And so the 2 things are now separated. And you have to figure out a way to associate an unbound star back with the compact object. For the really, really young supernova remnants, you don't need to know anything other than where the neutron star is. And so this is Cas A again. And so there's the neutron star. That's the center of the supernova remnant. So neutron star has drifted a little ways off. This circle, which is about 30 arc seconds, is how far a star could move away from the explosion site at 1,500 kilometers per second. Remember that typical walkway velocity was less than 30 kilometers per second. And so basically, to limit whether Cas A was an unbound binary, you really only have to look in this little tiny region here. Okay, and you can see it's also empty. And once I sort of looked at this, you said, oh, there are these other 2 young supernova, which we know about, namely the Crab and 87A. And you can do the same exercise. And so neither Crab or 87A were unbound binaries down to a few tenths of a solar mass companion. It's a surprisingly obvious statement, but for some reason it hasn't seemed to have been made before. Just one of those odd little gaps you run into. This does have some interesting things. So a popular model for explaining how 87A exploded as a blue supergiant is to make it a merger remnant. This idea was advanced very shortly after the explosion by Podsiadlowski. And then the other one is this business about how I ended up with this, that Cas A is known to be a type 2b supernova from the dust reflection spectra of the explosion. But to be supernova are generally believed to be binary mass transfer systems, except Cas proves there has to be some other channel because Cas was not a binary when it exploded. Okay, now if you wait older, then your search region gets a lot bigger. And of course, if you have a big enough search region, it's going to contain stars. And so if you want to go to older supernova remnants, things which are 10,000, 20,000, et cetera, years old, you need to have at least proper motions of the stars. And if you want to make your life easier, you want to have proper motions of the neutron star. So if you want to just stick to proper motions of the stars, you have to be able to define a center of the supernova remnant, some uncertainty in the center of the supernova remnant. So constrain the site of the explosion, and then you use the proper motions of the star to ask, could this star pass through the explosion site in some reasonable time? And so there have been a series of studies doing that. And the most interesting one is this one by Dinsel in 2015, where they report one candidate. The other two reported candidates, but we're going to diss them in a few pages. The somewhat cleaner way, because you don't necessarily have to worry too much about how well defined the center of the supernova remnant is if you also have a proper motion for that says pulsar, but neutron star, because then you can do the question of, can the motion of the star, the back motion of the star and the back motion of the neutron star intersect somewhere reasonably close to the center at some reasonable time? And so you just have a much more constrained problem. And this was done by Fraser for Crab, Cas, and Vela. And so they did their own confirmation of what we did for the Crab and Cas just by not seeing anything there. And then they also only found very, very low mass or low luminosity candidates for Vela. And then what we did is we took the 10 supernova remnants from our previous study where the neutron stars also had proper motions. And we also, that included the 3 where there were binaries. Basically, Gaia gave you the proper motions of the binaries, so you could also look for triples. Okay. Now, one problem with this is if you look hard enough, you're always going to find a star that is a candidate. And so you need some way else to evaluate not just whether you have candidates, but the probabilities of things being false positives. So a first question you might ask is, can you in any way limit this to find tight binaries? In some sense, right, is the stars which are going to interact or likely to do anything in the future are the things which are in relatively compact orbits, whereas wide binaries can extend out to almost 10 to the 5th AU or so before they get stripped by the galaxy. And the answer is no, you really can't preferentially select compact binaries. And here are just the numbers, just to give you the scale, right? A 10 to the 4 AU binary at 1 kiloparsec is 10 arc seconds across. If you ask how far or what proper motion you have to move 10 arc seconds in 10,000 years, a fairly young supernova remnant, that's a milliarc second per year. And the typical proper motion uncertainties on a good day for this problem are about 1/10 of a milliarc second per year. And so basically, if you allow ages of many tens of thousands of years, you have to have the uncertainty of the proper motion of both the neutron star and the Gaia star. Basically, you are limited to just saying any sort of binary out to sort of very wide binaries. You can't ask for compact binaries versus these very wide binaries because of the uncertainties in the proper motions. All right, false positives. So here are 2 games you can play given Gaia to try to get an estimate of false positives. So you can just get a sort of general assessment of whether the region of whether a particular supernova remnant is going to produce false positives by keeping the positions of all of the stars you're looking at fixed, and then randomly reassigning the proper motions. Okay, so basically you're going to ask is, given a sort of semi-random set of positions, which are going to be uncorrelated with the velocities, if I assign them a typical velocity for lots of other stars in the region, will they produce a candidate? Okay, and it depends on the supernova remnant. So, okay, it depends a lot on whether you have a parallax to the pulsar. So if you have a parallax to the pulsar, you do a lot better because there just aren't as many stars close to that you need to consider, right? If you also know the exact distance to the neutron star. If all you have is these sort of typical, very crude distances to the supernova remnant, then you have a much wider distance window for which you pick up stars, and you're much more likely to get false positives. The other way you can do it is if I have a particular candidate, okay, you can evaluate it specifically by assigning it proper motions of other stars of similar distance and magnitude. All right, why the similar distance and magnitude? Well, it's that kinematics depends on the distance. So if you put it at the star at a very different distance, it has different kinematics. And magnitude, because magnitude is luminosity. Luminosity is something about mass and age, and the kinematics of stars depends on their age. And so by limiting it to stars of similar distance and magnitude, we're sort of trying to say as well, it's at least to use stars which probably have similar velocity properties. And the two are not quite the same, because you could have, in theory, you could have a supernova remnant that is quite susceptible to producing false positives, but the particular one you found is very unlikely to be a false positive because the kinematics it has in order to produce the intersection is just weird compared to all of the other stars. Okay, so it's not mutually exclusive that it will produce a lot of false positives, but the particular one you find is fine. The bottom line of the false positives is if you look for low enough mass, meaning low enough luminosity, meaning more stars, every supernova remnant is always dominated by false positives. And that was basically what's happening with most of the reported candidates in those other papers, is they'd simply gone to, these supernova remnants are basically close enough that you can see all the way down to M dwarfs and things. And basically, by the time you get to those very low mass stars, you will eventually find a star which can have the kinematics to produce an intersection. And so basically, is they were operating at luminosities and masses which are low enough that you are guaranteed to have false positives. The one which survives any false candidate test you care to impose is the guy found by Dinsel. So that one looks like it's real. Unbound triples are the same game, right? Instead of trying to run back, one star and the neutron star, you run back 2 stars and the neutron star. Or in the case of the binaries, you're looking for a triple in which a binary remained bound and the 3rd star went unbound. And there are no candidates for either completely unbound triples in the case of the ones which are not binaries now, or unbound triples where partially remained as a binary in the case of the 3 binaries in the supernova remnants. Okay, so then you can have fun with the multinomial theorem, multinomial probabilities. So you get to combine all of these different numbers. So you have the fraction of supernova. So this is limited to neutron stars. Okay, so we're going to throw out SS433 because we can't do this for black holes, because the only ones where we can identify the compact object is if it's a neutron star. So you have the fraction of supernova producing neutron stars that are not binaries when the thing explodes. Then you have the fraction producing unbound binaries. You have the fraction producing bound binaries. And then you can split that up into the fraction producing interacting binaries and the fraction producing non-interacting or passive binaries. And so all of these are as a fraction of these stars which explode to produce a neutron star. And if you put together all of the sort of these 3 kind of whatever you want to call them mini surveys we did, you end up with this marvelous little expression for the probability distribution of these variables. And it just has to do with how many things we looked at and how many we found. So, right, we found the 1 unbound binary from the Dinsel star, so you get the fraction of unbound star at once. We have the 2 neutron star interacting binaries, so you get this one squared, and then these have to do with all of the non-detections. And so then you can, do your favorite way of doing this. But the bottom line, with big error bars, because you're not doing this with, huge statistics, you get that 76% of them were not binaries when they exploded. 10% produced a bound binary, 13% produced an unbound binary, 6% produced an interacting binary, and less than 9% produced a non-interacting binary. And then for the triples, you get that less than 18% produce unbound triples, and less than 50% of those producing interacting binaries can be unbound triples. And it gets messy because, as you see, the outcomes have quite a number of possibilities. But it is for the first time is instead of having only various binary population synthesis versions of these numbers, you actually have a measurement of them, albeit at a precision you would like to do better for. But. All right, so what about this Dinsel star? There's its ID number. It's a Draper star, HD 37424, and that's the Supernova Remnant. It's a 26,000 Kelvin B star. It's got a luminosity of about 17,000 solar luminosities. If you try to stick it on isochrones, it's something like 13 odd solar masses. You can work out its velocity in the plane of the sky. It's about 95 relative to the local standard of rest. You can do the same along the line of sight. So it's mostly moving in the plane of the sky. And there are a bunch of arguments suggesting that the orbit would have been in the plane of the sky. So one is just that the velocity of the star is mostly in the plane of the sky. There's also kind of a cool paper by this Yao et al., where they're basically looking at scintillation of the radio signals from the pulsar. Okay, so the remnant here is a pulsar. And from the properties of the scintillation, they were able to deduce that the neutron star still had to be relatively close to the center of the supernova remnant along the line of sight. So that suggests the neutron star also doesn't have a large line of sight velocity compared to its tangential velocity, which is several hundred kilometers per second. And the last one is it's got a pulsar wind nebula, which is seen edge on and perpendicular to the proper motion. And that also suggests the motion is mainly in the plane of the sky. Okay, so you can then actually try to limit what the property of the binary orbit was before it exploded. Again, this is not from the back propagation of the motions for the same reasons I mentioned before, is the uncertainty in the semi-major axis from the minimum semi-major axis from trying to back propagate to the intersect is very inaccurate. All you get is that it's less than 30,000 AU. Okay, but put the orbit in the plane of the sky. You have the velocities of the star and the neutron star, which you can put into the local standard of rest. You assume a statistical constraint on the pulsar kick. Again, you tried several, but it doesn't make a much difference, but you use this 265 kilometers per second. You can constrain the kick direction so that it has to produce the typical alignment of a pulsar wind nebula with its proper motion. This is an old argument by, I never can remember how to pronounce the NG name. Someone can yell it out if they remember. And Romani. You have constraints on the mass and radius of the star you see from fitting its spectral energy distribution. And I didn't do a formal analysis, but basically there aren't any massive stars in the vicinity. And so that suggests that the progenitor of the thing that did explode was less than 20 solar masses. All right, so you can try to put this together. And so here are two versions. This is the mass of the star, and this is the mass of the progenitor of the thing which exploded. Oops. And from the spectral energy distribution, the star is somewhere around in this range, and the progenitor is probably below this. It's a sort of a generous box for where it was probably sitting. And then the curves are the semi-major axis of the orbits, which you get. And they're all allowed, okay? It's not constrained, but you can sort of see is for the allowed mass range, you wanted an orbit at the time of explosion, which is something like an AU or less. There's like a 30% scatter in the allowed values at any particular point. But in that sense case, it's very hard to make the thing at explosion bigger than even 2 astronomical units. Very close things are ruled out. If you're below this red line, then the star we see would have been inside the Roche limit of the star which exploded. And if you're below this dashed line, you have problems with this alignment of the pulsar wind nebula with the direction of motion. And that basically is, it's not a brilliant measurement, but the thing was some fraction of an AU separation when it exploded if you try to put it back. The other panel shows what the Roche limit would be from the star we see on the progenitor, which exploded. And you can see you're getting 10s to 100 solar radii. Okay. Well, a red supergiant would be 500 or 1,000 solar radii. And so a sub 20 solar mass star would usually be viewed as exploding as a red supergiant, a type 2p supernova. But there is no way that if this is real, these things could have been separated by the radius of a supergiant. And so this must have been a mass transfer system. And the mass of the star we see has been enhanced the mass of the star that exploded was partially stripped. It is far enough separated that it doesn't have to be fully stripped. And so presumably this thing, when it exploded, was an interacting mass transfer binary. And you would expect the supernova to have been another one of these type 2b supernova. It's not. The type 2b's are a non-trivial fraction. They're like 12 or 13% of supernova. So invoking it is not wildly unlikely. It's not wildly likely either, but those are the tea leaves you can get. Okay, so let me now talk about the progenitor of Vela. So the advantage of Vela is that it's very nearby. It's 286 plus or minus 16 parsecs with a direct VLBI parallax. And that's very close, since with Gaia, you can literally select stars in a sphere around Vela of whatever radius you want to select. And so you can select stars in a certain radius. You can model the CMD of the stars to determine local star formation history, and you get the probability distribution for the age of any star dying to form Vela. I won't talk about it at all, but you do have to account for extinction, and so that was all done. Okay, now there's one little fly in the ointment, and it's this guy, Gamma2 Tuvel, Regor, although Regor is evidently not an official name. It's the only massive star near Vela, and it is just over 100 parsecs from Vela. So when I was originally going to do this analysis, I was going to use 100 parsecs as my sphere, and then having the only massive star sit at like 101 parsecs, I shifted the standard analysis to include Gamma2 Tuvel. It is the nearest Wolf-Rayet star. It's a 29 solar mass O star with a 9 solar mass Wolf-Rayet star. It probably started with the mass reversed, and so the O star gained mass as the other star got stripped. It's actually a quadruple system, so it's in a wide binary with Gamma2 Tuvel, which is a lower mass system. It's a member of a compact star cluster of pre-main sequence stars, which will be important. And so the results I'll show is until I get to the end is what you get with Gamma2. So one thing you might ask about, since you sort of have most of the information, is you can ask about the completeness and contamination, right? I'm going to evaluate the properties of stars in a sphere around Vela today. But you can ask is, if I put that sphere sometime in the past, would I have the same stars, and how many stars, how many of the stars within 100 parsecs of Vela now were within 100 parsecs of Vela 10 million years ago? And if I go back 10 million years, how many stars which weren't in that 100 parsec sphere are there now? And of course, you have to run the clock backwards, to mimic, with the real calculation you want, which would be to run it from, when it was born to where it exploded, but you can run it backwards. And for a typical time scale of 10 to the 7 years, which is the lifetime of a 20 solar mass star, and the properties of the proper motions, a typical motion of the stars, the typical random motion of a star near Vela over 10 to 7 years is about 50 parsecs. And so if I take 100 parsecs around Vela now, it has 152 massive stars, which I have defined somehow I'm not going to explain. And if I go back 10 million years and I ask how many of those stars would be inside a sphere centered at the median position of those stars 10 million years ago, it's a third of them. And if I ask how many stars which were not in the sphere end up in the sphere, it's about 21%. So that's not bad. You get about a third of the stars that were actually born with Vela, and a minority of the stars are stars that were further away. If you increase the size of the sphere at the back time, so if you essentially in the forward direction, if I analyze a bigger and bigger region, I will include more of the stars which were originally within 100 parsecs of Vela, but my contamination goes up. And so if you go to 150 parsecs, I now have 2/3 of the stars that were within 100 parsecs, but half of the stars are interlopers. When I go to 200 parsecs, I can now encompass 84% of the stars, but 2/3 of them are interlopers. And this is all for 10 million years. If I go to the lifetime of a 10 solar mass star, which is 3 times longer, right, all of this gets worse, right? They now have a typical motion of 150 parsecs. And so the fraction of stars in a 100 parsec sphere goes down and the number of interloper stars goes up. So this is something to keep in mind about this. All right, so here's this color magnitude diagram of the region. And so the points obviously are the stars. There is our friend Gamma2 Tuvel. You can see it is well separated from the isochrones associated with anyone else. But you can see that the main sequence kind of peters out, and there are sort of no other high mass main sequence stars going from here up to that guy. And so that's sort of a signature, is that Gamma2 is a bit of an outlier. This is sort of a last isochrone, which you would expect to have stars exploding. Right? So this is this sort of 10 highest mass on the isochrones, about 10 solar masses. These down, once you get below that, these are stars that are not going to explode. And you can sort of see is that somewhere around this region is where you see the last main sequence stars. And so just by eye, right, you're sort of seeing is that Vela wants a low mass progenitor, except for the question of what Gamma2 is going to imply for him. Okay, so you can model that isochrone in terms of ages of the stars. So you chop up time into logarithmic bins. You can then, by fitting the CMD, try to assign the stars on that diagram to various ages. And so here's that distribution with the medians and their 90% confidence ranges. All of these error bars are hopelessly correlated, so don't try to interpret them directly. And the interesting thing is you can see that in this bin, which is right around 10 to the 7.5 years, that is where it wants to put the vast majority of the youngest stars. Okay. And if you ask what mass range that corresponds to, it's sitting there right at the bottom of the mass range where you expect supernova from nominally 8.1 to 10.3 solar masses. Okay, you can play some games. You can ask, how many stars did I form which were more massive than a solar mass, which is the variable to actually fit? And that moves all the numbers up. It also, right, here, the number of stars I see is dominated by this guy because I'm only seeing these lower mass stars from the fraction which are up at the tip of the red giant branch. Right? If I actually correct to the number of stars above one solar mass, these go greatly up because now I get all of the lower mass stars which have not moved up the giant branch. Okay, and so this little bin of stars is not dominant by number. Okay, it's dominant by the number of higher mass stars. Okay. And you can do some sanity checks on this. The total number of stars is for Krupa IMF is 11 times the number above one solar mass. If you turn that into a local stellar density, you get a local stellar density that is very consistent with direct, people who are directly estimating it locally rather than trying to do this weird calculation I'm doing, which is pretty remarkable given that the mass is all down here. And the correction from those things at the tip of the red giant branch to the total mass is big. It's like a factor of 30,000. All right, we can also then turn this into a star formation rate. And again, you see the star burst associated with this lowest mass supernova-like bin. And if you want a sense of scale, the numbers are in the number of stars above one solar mass formed per megayear. And if you want to turn that into a sort of a global galactic star formation, 10 per megayear is a star formation rate of about 0.04 on the galaxy-wide basis. This is up about 6. And so the starburst, is about a quarter of a solar mass per year. So it's not a super big starburst by a galaxy standard, but it really does want a lot more star formation here than these other bins. You can ask how well you got the distribution in mass. So this is the distribution in mass from the CMD. Actually took all of the stars above 10 to the 3.5 solar luminosities and modeled them individually. And this is the integral distribution of the minimum allowed masses for them, the integral distribution of the maximum allowed masses. Here's our friend Gamma Vel sitting out here at the end again. The fits to the SCDs and then matching them to isochrones have a degeneracy between mass and age. So these high mass solutions correspond to younger ages. These low mass solutions correspond to older ages. The CMD fits have a definite opinion about the ages, and they like the stars to be this old and not that young. And so that's why the models kind of go right through the lower edge. It's because because the CMD fits are better at determining ages than fits to individual stars. Oh, and the final thing is you do have to undershoot Gamma2. Basically, is there just aren't enough stars in here to have the predicted curves go through Gamma2. Gamma2 is not wildly unlikely, depending on exactly how you want to do the calculation. The probability of this star formation history leaving you with a star like Gamma2 is something like 10 to 25%. Okay, so here's sort of the final answer. If I'm analyzing only a single supernova record remnant, I can't tell you anything about the minimum mass for explosion. Okay, I just have to put that in by hand. And so for this purpose I just said that the lowest mass things that can explode are that 8 to 10 solar mass bin. And here now is the integral distribution of the probability of the ages of the stars which explode. Okay, so it all goes to 1 because a star has to explode. So by the time I get to here, it has to be 1. But it's now as a function of the sphere I use. So here is my original 100 parsec sphere. And here's the consequence of going to 125 parsecs, including Gamma2. So suddenly the chances of a higher mass jump by an order of magnitude. Although even then, something above 20 solar masses is still less than 10% likely. And so it seems to strongly argue that the progenitor of Vela was relatively low mass. And if you really just stuck to the 100 parsec sphere, you would really want it to be assigned to that lowest mass bin at sort of 90% confidence. And as I said, is there risks in using this to estimate individual progenitor masses? But the tea leaves are is that the progenitor of Vela was almost certainly under 20 solar masses. There's another reason why the high mass solutions for Vela are disfavored. If you remember, I told you that Gamma2 was actually in a compact cluster. And so to make Vela associated with Gamma2, right, it has to have gone flying away from that cluster, which is a distance of 100 parsecs. And so it has to be a runaway star from a disrupted binary if you want to associate it with the star formation leading to Gamma2 Vel. And if we take those Renzo models of the velocities of these runaways, it is plausible that a low mass star could explode 100 parsecs away and get to where Vela is now. So for their velocity distributions, there's a 20% chance that a 10 to 15 solar mass runaway star could move 100 parsecs before dying. 5% chance for 15 to 20 solar mass, but it becomes very unlikely for the higher masses. So it is a high mass progenitor is disfavored, both because there aren't very many high mass stars, but it's also disfavored because if I did it, I would have to associate with the Gamma2 cluster. And if I did that, it can't be a high mass star and get to where Vela is now. And so it gives you a second argument, is that it's just kinematically improbable to do that. You can also do a little cautionary tale. Since I sort of have 3D information, I can redo my selection thing to mimic what people do in the extragalactic surveys. Is I can take a 50 parsec sphere around Vela and then look at it from above the galaxy and ask what would I see in a 50 parsec cylinder, looking down at it as if I was in an external galaxy. And so if I do this at 50 parsec sphere and a 50 parsec cylinder, the cylinder contains 47% of the stars in the sphere, right? You gain because if you drift upwards, you're still in the cylinder. But 80% of the stars in the cylinder were not associated with the sphere. If I go to the lifetime of a 10 solar mass star, that changes to include only 11% of the stars which are originally within 50 parsecs, and 90% of the stars are contamination. And so, as I said, is you should worry a little bit about individual mass estimates for the three-dimensional selection because of contamination. But the contamination in 50 parsec spheres for these extragalactic things, at least based on the Vela, are very, very high. And you should really worry about any attempts to do individual progenitor estimates for external analyses of stellar populations around external supernova remnants or supernovae. I just mentioned a related topic is the other way you can try to get a handle on some of these questions of binary evolution is to try to look for non-interacting compact objects, which is something we've taken up in the last year or two. Again, it's that the interacting binaries and mergers are a tiny fraction of the compact binary population. They depend on things like common envelope. But you can sit down and try to start systematically looking for non-interacting binaries. The two you can do right now is that SDSS Apogee and other spectroscopic surveys are providing sparse radial velocity curves for hundreds of thousands and soon millions of stars. And so you can try to select out ones which show signs of high mass companions, high mass dark companions follow-up. You can also take a survey like our assassin variability survey and look for ellipsoidal variables, which seem to be dark. And eventually, right, Gaia will provide astrometric binaries. The devil we found, I mean, we have two candidates which no one has killed yet. They're a little bit annoying because they're around giants, which makes your life hard. And the inferred mass of the compact object is around 3 solar masses, which puts it kind of essentially at the upper limit or in the nominal mass gap between neutron stars and black holes. So far, no one's managed to kill them off. We're still doing some follow-up observations. And then we have 2 more candidates we're pursuing now. The sort of problem you get into, particularly for these lower masses, is what we like to call the binary swindle, which actually dates all the way back to when Kip Thorne and Virginia Trimble originally thought about doing this in the early 60s, which is a way to make your companion darker is instead of making it a single star, you make it 2 equal mass stars. And because of the steepness of the mass luminosity relationship, you reduce the luminosity of your companion considerably, and you make it cooler. And so it tends to be easier to hide it under the spectral energy distribution of your companion. And so that's some problems like that will continue to exist even once Gaia, Gaia simplifies some of doing this sort of search, but it doesn't get you out of some of the complications of follow-up. All right, let me just sum up with where you might go from there. A big problem is more X-ray observations. The 49 we initially targeted, all of them could be improved to actually identify their compact objects or measure more proper motions. And the most common problem is, yes, there's X-ray data, but things were getting faint enough that you now have 10 X-ray sources in the Supernova Remnant, and no one's sure which one might be the compact object. Many of these observations are over 10 years old, and so redoing the observations to look for the X-ray source which moved will be a plausible way of both identifying the correct compact object and getting the proper motion, which would help to do the binary searches. Not all of these should have a neutron star remnant, right? Some of these are type 1As, and some will be non-interacting black holes, which you can't find either. The other big problem in all of this game is that the distance estimates for supernova remnants are just horrible. At best you get things like 1 to 2 kiloparsecs for the distance, and even then, as someone else will say, it's 0.5 to 1.5 or something. And if you have these big distance windows, all of your problems of contamination and become much, much worse, obviously. There is a straightforward solution, even if you can't get a direct parallax to the compact object, namely that the supernova remnant produces absorption features in background stars. And this was done for Vela actually a long time ago. And even using Hipparcos parallaxes, Cha et al. Got a distance to Vela within 1 sigma of the geometric parallax, basically just based on when the stars started showing high velocity absorption features. It's also interesting that the absorption features in these stars, the high velocity absorption features change very rapidly. Is Rao and company have been following them up in the intervening decade, and the structure of the absorption is constantly changing, which might make it an interesting probe of the supernova remnants. Triples, funnily, are easier than binaries. Triples, you get to use 2 stars with Gaia parallaxes and proper motions. And having 2 stars that you have to back propagate and intersect at the same time with something else is a really strict requirement. And so in fact, it's relatively easy to significantly expand the number of systems searched for triples and improve those limits, just because having the 2 stars instead of the 1 star makes life so much easier. Progenitors, the main issue just is, again, the supernova distance. That Vela is easy because you got the geometric parallax of the pulsar. You can literally pick stars within 100 parsecs. And you can do this for the Dinsel star, which also has the neutron star, also has a parallax. You can do it for those 3 interacting binaries where Gaia supplies a parallax to the star in the binary. However, there is one interesting, is my first thought on doing this was to do SS433 because it's a black hole, dominantly. But there's an interesting problem that the Gaia distance, which is in the regime where Gaia distances are getting flaky, is 6 to 14 kiloparsecs, but it is in significant disagreement with estimates from the kinematics of the SS433 jets, which are smaller. And we had some discussions with people who know this about whether the parallax, there were any evidence for problems in the parallax. And the answer is not really. We had some conversations with the people who did the kinematic models, and they basically said there's no way it's that far away. And so at the moment, that just remains a puzzle. And that's all I was going to say.
Thank you all, Chris. Nadia, please go ahead.
So I thought you were going to tell us what, so I'm getting the feeling that the binary fraction of the progenitors seems to be very low compared to what I would have naively expected from just the feeling I have about massive stars, right? Where we're taught that they have tens of percent, 50% binary fraction, and they have close to equal mass ratio. So what are your thoughts on how to reconcile what you guys are seeing with these sort of ideas, and can they just merge before they explode?
Yeah, so let me go back to that Renzo figure. Is it still shared?
No.
Okay, I think I have to. Okay, so if you go to this so you've lost sort of 20% already by the time so there's the intrinsic binary fraction, which admittedly is maybe close to 100%. There's the fraction you lose due to mergers. Okay, so let's say you made them 75% binaries, then you lose that amount there. But the other thing that's missing from here is these numbers are not accounting for the fraction of explosions, which are explosions of secondaries, right? That if you're looking for the searches you can do are for things where you've seen the explosion of the primary, but the supernova remnants you're looking at include explosions of both primaries and secondaries. Okay, so the fraction of things which are not explosions in what I've done, right, is reduced because of the fraction of things which were explosions of secondaries. And so that's a lot of the difference. So there is some just from fraction of binaries and fraction of binaries which survive would explode, but then there's also the problem is that the experiment you can actually do, you're not limited to looking at first explosions, you're looking at first explosions plus second explosions.
And what about any other type of contamination, like type 1As? Can you filter out the supernova remnants that are other types, or is there a possibility of additional contamination?
So you can do some typing of supernovae, and so the ones which had clear evidence of being supernova type 1As we did remove. You can roughly estimate in those 49 how many more might be 1As, and so we tried to do a correction for that. But basically, the games for trying to tell the types there's the work by my colleague Laura Lopez, where you can try to use the symmetries of the supernova remnant to distinguish them. So 1A remnants are more symmetric than core collapse. And the other is if you have X-ray abundance estimates, you can distinguish between them. But neither of those are available in sort of a uniform, any sort of uniform survey of these things. And so you can't simply apply it across the board, unfortunately. But you can try to make a correction for it. I remember that the core collapse really do dominate the supernova rate by a factor of 3 or 4. Right? The other reason why supernova surveys find mainly 1As is they can find them further away because they're brighter. But the intrinsic rate of 1As is much less than the intrinsic rate of core collapse.
More questions from the audience? Yes, sir.
So I'm just curious whether the property of the supernova remnant, for example, the shock speed or single transmission, have any connection to the progenitor property?
So when people worry about that, the answer is not well enough to do you much good. And part of it is, yes, these things depend on energies of explosions and velocities, but they also depend on the mean density of the interstellar medium, which can be hard to measure. And so no one has really managed to use the properties of the shock per se to distinguish them. There is this game from using the shape of the shock wave, where the 1A shock waves tend to be more spherically symmetric than the core collapse, but not directly from the shock properties. The abundances, the X-ray abundances can do it, right? Because the core collapse produce oxygen and 1As produce iron.
Okay, can I ask just one really minor clarification question on the previous and on this exact diagram that's showing right now? So you said that in your sample, there's potentially a contamination from the supernova remnants from the secondary, but what about the supernova remnants from the stellar mergers?
Yeah, so yeah, I mean, they're contaminating too, but they would just be singlets. Yeah.
Okay.
Yeah, no, so one chain of supernova remnants, which will not have things, is there's the fraction which were not binaries, and then there's the fraction which merge. So that's one route to, there was never a binary companion to look for when it exploded, and then the other route is the explosions of the secondaries.
We have a couple of questions on Zoom. So Tere, could you please unmute yourself and talk?
Hi, Chris. Thank you so much. This was very interesting. I just wanted to ask a question about the final sample of remnants that were used to get the statistics that you presented. So is it the 23 remnants that you mentioned that are included in that? And
yeah, so Katie was responsible for picking the 49, and I'm blanking on exactly what the rules were right now, but then of those 49, 23 had identifiable compact objects. Okay, so in theory, that's fine for looking for whether they're bound companions. The one issue we did worry about is, so it's not obvious, if the system is not interacting, it is not obvious that the detection or non-detection of the compact object has any effect on whether or not you find a companion. So we think it is safe to say is that in searching for a bound companion to the single compact objects, it's however many you got out of the 23, which was 0. There are also, however, the 3 interacting systems. And it seems at least likely that interacting systems are just so easy to find that you found all of them that were in the original 49. And so basically for this, we give several versions, but I would say my default assumption would be is that all of the interacting systems in the original parent system are found. And so there you're really doing the 3 out of the 49 minus the 1As, not 3 out of the 23 where the compact, had identified compact objects. So
yeah, I was just to follow up. I was wondering about the final selection and whether you somehow had to limit it by the age of the remnant. I did read your paper in detail, but now I can't remember what the final list of remnants were. There are a number where there are compact objects detected, but they have moved quite far from the explosion center by now. And I'm wondering if those have much larger uncertainties on where the explosion center was and whether you had to exclude them. So is there something about the sample that, like some common property that, based on age and things like that?
Okay, but remember, for the one search is you're just looking to see if the compact object has a companion. It doesn't really matter if it's moved or not, right? The one issue, if you want to worry about the statistics, it would be is it actually unassociated with the supernova remnant? So for the analysis of looking for the unbound binaries, we used only the ones which actually had proper motions. And
okay.
Yeah, there is a lot of murkiness in exactly how you're doing here, what you're doing here, in part because sorry to throw stones at your field, but oh my God, I don't want to look at supernova remnant papers ever again. It's such a mess.
No, I hear you.
And then there's a question is, that the visibility of the supernova remnant, depends on background densities, explosion properties, and so forth. I think what is probably safe to say now is that the statistical errors are bad enough that you're not worried about systematics yet. If we can get to a point where we're going to have to, where the statistics are good, then yeah, you're going to have to figure out all these systematics. But I think it's not there at the moment.
Thank you.
Wenbin?
Oh, hi, Chris. I want to ask about these interacting, the remnants that are interacting.
Mm-hmm.
So I think these ones are most likely the case where before the supernova explosion, they're already interacting. Is that correct or is that incorrect?
They're fairly wide, so they are wind. They are even before supernova. Well, you don't know exactly what the orbit was before, but anyway, at the moment they're wide enough that they will only be wind accretors.
Oh, they are only wind accretors. There are no Roche-Lobe.
Yes. Well, so what you don't know is whether the progenitor was Roche-Lobe overflowing onto the
survival. Yeah.
The companion stars are just main sequence stars, but
there is no remaining signature of past interaction at all, I would say.
It's tricky because if you could look at things like rotation, except it would be the thing which exploded, which would end up being like tidally locked. So the rotation velocity of the thing you see may not be telling you anything. You can look for contamination on the surface of the star.
Mm-hmm.
So there are HMXBs where the companion star shows odd isotopic anomalies, but those are believed to come from debris from the explosion. So again, that doesn't tell you about what it was doing beforehand.
Yeah.
So I'm not sure. I'm not sure we have any real handle on what it was doing before exploding.
It would be really useful to kind of know whether there was interaction between the binary before the explosion, because all these supernova observations, they show CSM interaction, and whether some of that interaction maybe is related.
So, personally, I don't agree with that bandwagon. I think the bandwagon for CSM interactions is misinterpreting something, because in another hobby, we have light curves of stars before they explode.
Mm-hmm.
Type 2b supernova. They aren't doing anything. If they were doing anything like what people are claiming for these pre-supernova CSM things, it would be so obvious that,
Yeah,
that,
I see.
If you take a star and suddenly turn on a 10 to the -3 or 10 to the -4 solar M-sun per year wind, that star vanishes behind a wall of dust in about 30 milliseconds.
Yes. Mm-hmm.
And
yes.
they ain't doing that. I mean, we can typically see 10% changes in the progenitor. And basically we aren't even seeing, we are barely at the, we aren't even really seeing good evidence for like Betelgeuse level RSG variability, although we are maybe slightly too insensitive to see normal RSG variability. But it would be good to get more of them. We originally really liked this idea, as we said, oh great, we used to call them, we'd be able to put circles of death around stars, but so far not. It'd be good if some more stars. It'd be good if more stars in the LBT sample exploded, but for some reason, all of the galaxies have gone on strike since 2017. And sort of having a mean supernova rate of 1 per year, and then 2018 came and they said, forget it, we're not doing supernova anymore. It hasn't been 1 in 3 or 4 years.
I see. Thanks.
Are there any more questions? Yes, Nadia.
Okay, one last one. So can you repeat again why for these kind of transitioning type supernovae, the ones that go from 2 to 1, why is it a strong indication of binarity? And is there an alternative explanation that doesn't involve binarity for those?
Well, okay, so so the physical picture, right, is your left. You have you want to somehow remove almost all of the hydrogen envelope. So you want to leave a very thin veneer of an envelope, like under 1/100th of a solar mass of hydrogen or something, and that actually is still enough that the thing looks like doesn't turn into a blue star or anything. In fact, the progenitors of 2Bs, which have been seen, are actually yellow stars. But anyway, you still have a big puffy hydrogen envelope. It just has no mass in it. And then when you explode it, then the veneer sort of gives you a hydrogen signature for a little while, but then basically you see the interior and you get helium instead. And it's just that the people who try to do this don't like trying to do it by single star mass loss. I mean, in some sense, it's sort of a bit of a fine tuning question is how you do it. But they can get plausible models where you transfer it to a binary companion. In some sense, I guess the way to think about it is there's no characteristic scale at which to stop a wind, right? But the orbit gives you a characteristic scale for controlling mass loss. I think would be the way that sort of character, there's sort of why the two things would be better or worse at trying to produce this sort of thin veneer scenario. But basically, essentially all published models for the 2Bs depend on binary mass transfer, but apparently there really is another channel. Because the Reston company have, they've actually got multiple spectra of Cas A. It's sort of fun is you get spectra of the supernova from different directions, depending on where the dust is. And so you can actually see how supernova spectra would change depending on which direction you're looking at it from, which is fun.
All right, so I think that's it. So thanks a lot. Thanks again, Chris. And we're going to have a group discussion in 1 hour or so we can start, I guess, maybe slightly later, like 1:10, and ask some other questions and discuss other topics.
Okay,
Yes.
see you then.
So
Yeah, see you.
see you. Thanks.
Thanks a lot.